Welcome, everybody. I have the pleasure to give you the welcome in Padua and for this very important conference of EAS 2024. And this is the opening ceremony. I am Micela, one of the co-chair, together with Bianca Poggianti of the scientific organization of the meeting. So it's a pleasure to me to present this session. In particular, we start with the president of EAS, Roger Davies.
Thank you very much, GC. My name's Roger Davies. I'm the president of the European Astronomical Society, and this is the last annual meeting that I will open. So I'm very much looking forward to it. Welcome to Padova. Welcome to EAS 2024. It's good to get together in the largest celebration of astronomy in Europe. I particularly would like to welcome the representatives of the region and the city of Padova. I will say a few remarks about where we are in a moment. So we have moved from Krakow last year to Padova this year, from Copernicus to Galileo. This reminds us of the central place the story of astronomy plays in the history of Western intellectual thought. That path was really important for changing the intellectual view of the world from received wisdom to inductive thinking. Their achievements span much more than astronomy. They revolutionized Western thought. So, Padova is a very special place. And let me encourage you while you're here, not only to enjoy the sessions and participate, but also to take some time to explore Padova. 300 years before Galileo pointed the telescope at the skies, Giotto painted the frescoes in the Scarini chapel. They are quite remarkable. I visited them yesterday morning. In the panel in that chapel showing the adoration of the Magi is Halley's comet, which Giotto himself saw in 1301. So it was another 400 years building on the work of Copernicus, a Pole, Tycho, a Dane, Kepler, a Czech, Galileo, an Italian, and Newton, a Brit, that Halley was able finally to understand the orbit of the comet. There is no better way of showing how astronomy is an international subject and always has been. Padova is now a major center, of astronomical teaching and research, with strands of work that cover almost every aspect of our subject. We're very lucky to be here. Thank you to the organizers, and do take advantage of being here. This meeting is huge. There are 1,773 participants, including about 200 online. In fact, this is the first EAS annual meeting which has been entirely online. There are 15 symposia, 41 special sessions, and 8 lunch sessions. In total, there are 1,149 oral presentations and 817 e-posters. That's almost 2,000 contributions. So let me just say now to everybody who's worked hard to do those contributions, thank you. This is an incredibly dynamic, vigorous astronomical community, and we're here to celebrate all your successes. I'd like to thank the scientific organizers, who we'll be hearing from shortly, Bianca Poggianti and Giuseppina, and the hosting committee led by Alessia, Moretti, and Marco Giusic, for the huge amount of work that they've done putting together this exciting program. Thanks also to the annual meeting board, chaired now for many years by Lex Kappa. They have once again succeeded in bringing our aspirations for this event to fruition. We shouldn't forget also the huge commitment on behalf of the staff of our partners in organizing this, Kuoni Tomle, They invest a huge amount of energy in this event, and without them, it would simply be impossible to put it on. The work that you've all done to make this celebration of astronomy possible is absolutely outstanding. We're about to experience the fruits of your combined labors. Thank you very much indeed. In in-person meetings like this, it's particularly rewarding for me to see so many young people so students and early career researchers. You dominate this group, actually. There is more students and early career researchers than anyone else. Use this opportunity to establish your networks and build collaborations, interact with colleagues and future colleagues, and promote your work. And hopefully you'll have some fun along the way. So what has the European Astronomical Society been up to in the last year? Well, you've elected two new councillors, Ignacio Ferreras and Sven Wedemeyer, bringing the council up to its full strength of 12. We grew the size of the council a couple of years ago by changing the constitution because we have so much to do and we needed a little more help. So welcome to Ig and Sven. I'm delighted that we have a new organizational member this year. Our organizational members are very important. They support us in a variety of ways. It's the Netherlands Nova Foundation. Thank you so much for joining. Your support is very much appreciated. And thank you to all our organizational members for their continuing support. Led by the working group chair, Robert Massey, and our vice president, Sara Lucacella, we've stepped up our efforts promoting the dark and quiet skies agenda to protect observational astronomy from the threat of satellite constellations. We are observers at the UN COPUOS meeting, the Committee for the Peaceful Use of Outer Space, and we were delighted in that group to support a successful proposal led by Spain and Chile to make the emerging threats to astronomy from satellite constellations a standing item on their agenda. We also joined ESA's Zero Debris Charter to address the escalating risk that astronomy faces, or mankind faces, from the increase of space debris around the Earth. Last year, we celebrated 10 years of the Merak Prizes. This year, the Merak Foundation has awarded a new prize, the George Lake Technology Innovation Award, in areas of new technologies, instrumentation, and computing. The €100,000 prize will be awarded in alternate years. In this inaugural year, the field was exceptionally strong. So strong that the foundation were persuaded to make 2 awards. So congratulations to Emmanuel Hugo from the Laboratoire d'Astrophysique de Marseille and to my colleague Boone Cocktan from the University of Oxford. We're grateful to the Merak Foundation for the increased support for the Society's work that we agreed with them in the spring. This year, we negotiated a new agreement with the University of Geneva, where we continue to host the Society's office and executive secretary, Marc Audard. I'd like to thank Francesco Pepe, the director of the Geneva Observatory, and our treasurer, Nick Kilafis, for the positive approach they took to negotiating this new arrangement. And I can confidently report to you that the administrative functions of the Society are in safe and capable hands. Before I come to my closing remarks, just 2 quick coming attractions. The second HERA workshop for young astrophysicists, sponsored by the Society and the Heraeus Foundation, is coming up. It will be held on the subject of the nature and dynamics of structures observed in galactic disks. That's from the 15th to the 20th September in Athens. There'll be a 3rd workshop next year. And also, now that the European elections are over, we can aspire to plan a 3rd event at the European Parliament, and we will hope to do that in 2025. So, as I said, I am stepping down as your president after 7 years, and perhaps I can be allowed to make a few personal remarks at the end here. So, among the large numbers of people here, we are celebrating the contributions of our prize winners to our subject. And at the other end of the career ladder, some of you here will be giving your first talk. I hope it's memorable. You'll be a bit nervous, probably, but you are among friends. This is a supportive environment. We all want to see you do your best. So good luck, enjoy your first talk. Whether you're senior or junior, this is your society. Our membership now exceeds 5,000. But for those of you who are not members, please do join and participate. If you're a member of one of our national affiliated societies, then membership is free. So the next time you come to renew your membership, just look out for that place in the renewal where you can tick a box to say, yes, I would like to be a member of the EAS, and you will become. For those of you who are already members, please come to the General Assembly on Wednesday here at 11:30 in the morning. This is your chance to have input into our activities and also to ask us probing questions. Okay, so I would now like to thank the entire council and those ex-councillors who served with me throughout my term. It is your commitment and enthusiasm that keeps the society going. We need people to step up and drive the society forward on the council. Thanks also to our small team in Geneva. This is a very small administrative team to run a huge event, or to run a huge activity like this, led by our outstanding executive secretary, Mark O'Dar. He is at the heart of all we do. Mark. I'm delighted that Council has elected as our interim president, Sara Lucatello of Padua Observatory. She will become our first woman president. Sara. It has been an enormous honor to serve you as president for 7 years. It's time for new leadership. I wish Sara every success in the role, and I hope she enjoys it as much as I have done. And I wish you all a very happy week. Thank you.
Thank you very much, President. Now, the Councillor for the Digital Innovation of the Veneto region, Francesco Calzavara.
Grazie, buongiorno a tutti. Vi porgo il benvenuto a nome della Giunta regionale del Veneto e del suo presidente Luca Zaia. È un onore e un piacere che sia stato scelto il Veneto, in particolare la città di Padova, come sede del congresso annuale. Credo che tutti sappiano il grande legame che la città di Padova ha con l'astronomia. Tutti sappiamo di Galileo Galilei e Niccolò Copernico. Entrambi trascorsero degli anni a Padova, ma già ben prima di loro, nel 1300, si insegnava astronomia nell'Ateneo Patavino. La scienza ha certamente dato lustro a questo territorio, ma lo ha anche reso capace di fare impresa e di generare innovazioni in settori industriali collegati.
Good morning, ladies and gentlemen. I would like to welcome you on behalf of the Regional Council of Veneto region and its president, Luca Zaia. It's an honor and a pleasure that Veneto, and in particular the city of Padua, have been chosen as the venue of your annual meeting. As you know, there's a great bond that links the city and astronomy. You all know that Galileo and Copernicus both spent years in Padua, but way before them, since the 1300s, at Padua University, astronomy was taught. The science has definitely brought prestige to this territory, also making it able to network and to become and to generate innovations in related industrial sectors.
La regione del Veneto è una delle regioni motore dell'economia italiana, quarta regione in Italia per PIL, terza per numero di imprese, prima nel turismo, terza nella manifattura. e grazie alla rete dei propri centri universitari e centri di ricerca negli ultimi anni si pone ai vertici dell'European Regional Innovation Scoreboard. Questo ha permesso di creare interessanti dialoghi tra il mondo della scienza astronomica e quello delle imprese e reso possibile la nascita sul territorio regionale di eccellenze industriali, come ad esempio per la produzione di ottiche, per la costruzione di grandi osservatori di infrastrutture, per la fornitura di servizi per il mondo delle multi-utilities, per lo sviluppo di software e di sistemi di automazione e controllo.
So the Veneto region is one of the drivers of Italian economy, ranking fourth in terms of GDP, third in terms of number of companies, first in tourism, and third in manufacturing. And thanks to the network of its university centers and research centers, it also comes top in the European Regional Innovation Scoreboard. This allowed us to create interesting dialogues between the world of astronomical science and the business world, and made it possible to create on the regional territory industrial in excellencies for the production of optics, the construction of observatories, for the supply of services for the multi-utility sector, for the development of software and automation and control systems.
Nell'ambito dell'agenda digitale del Veneto, stiamo investendo in diverse azioni per rendere il nostro territorio sempre più attraente per settori di punta come quello delle scienze astronomiche. Permettetemi di segnalarvi alcune iniziative. La prima, la nuova rete di supercalcolo, finanziata con 15 milioni di euro all'Università di Padova e a tutte le università del Veneto, per avere una nuova infrastruttura computazionale a servizi di modelli e soluzioni innovative per i diversi settori di ricerca. La seconda è l'investimento nella Space Economy, una rete di imprese venete rappresentata dalla rete innovativa regionale che si sta affermando a livello internazionale e assieme a loro abbiamo organizzato lo scorso maggio il secondo evento Space Meeting Veneto 2024 a Venezia, con più di 250 aziende, 150 buyer, 3.000 presenze e 6.000 matching B2B.
So, as part of the Veneto digital agenda, we are investing in several actions to make our territory more and more attractive for sectors like astronomical science. And let me just mention a few of these actions. The new network of supercomputation funded with 15 million euros to the University of Padua and the universities of Veneto for creating computational infrastructure. Then the investment in the space economy network of Veneto in businesses represented by the Regional Innovative Network that is establishing itself at an international level. And we also hosted the second Space Meetings Veneto 2024 event in Venice with more than 250 companies, 150 buyers, 3,000 participants and 6,000 matching B2Bs.
Inoltre stiamo investendo anche sul tema spazio e giovani, con la seconda edizione della Challenge Veneto Stars, quest'anno orientata all'utilizzo dei dati spaziali per la valorizzazione dei siti patrimonio UNESCO, un'iniziativa su scala europea che ha visto la partecipazione di oltre una decina di team internazionali, tra i quali abbiamo selezionato i 3 migliori per farli tornare in questa settimana in Veneto per sviluppare il loro prototipo. Abbiamo recentemente aderito al programma IRIDE dell'ESA, Agenzia Spaziale Europea, per inserire i dati spaziali nella strategia digitale della regione e nella Veneto Data Platform.
Also, we are investing in space and youth with the second edition of the Veneto Stars Challenge. This year, that will use space data to enhance UNESCO heritage sites. This is a European initiative with more than 10 international teams, out of which we have selected a few who will be back with their prototype. We've also recently joined the IRIDE program by ESA to enter space data in the digital strategy of the region and in the Veneto Data Platform.
Queste sono solo alcune delle iniziative che abbiamo in corso e sono emblematiche di come questo territorio abbia delle incredibili eccellenze, che però fa parte un po' del nostro modo di porsi, vengono non molto comunicate perché noi veneti siamo più abituati e impegnati a fare che a raccontare e a dire. E quindi stiamo cercando di migliorare con eventi internazionali prestigiosi come questi che ci danno la possibilità di mostrare a delegati e ricercatori da tutta Europa come la scienza sia centrale e sia un driver di sviluppo del Veneto e di una città come Padova.
So these are just a few initiatives that are underway and that exemplify our incredible excellencies, which, however, are not advertised too much because, as we are used, we are more for doing than telling or storytelling, let's say. But we're trying to improve in that aspect. We have international events just like yours. So we are very happy to have the possibility to tell our research and initiatives to delegates and researchers from all over Europe because science is an important driver of development of Veneto and a city like Padua.
Non mi voglio dilungare oltre e voglio nuovamente ringraziare EAS per aver scelto questa nostra città e il Veneto per questo grande evento e spero che naturalmente possiate portare a casa, oltre che un arricchimento personale di queste giornate passate insieme con grandi testimonianze del vostro settore, anche un buon ricordo della nostra città di Padova e della nostra regione del Veneto. Grazie a tutti.
So thank you all for being here. I hope you will bring with you also good memories of the city of Padua and of Veneto in general.
Thank you very much. Now, the Councillor of the City of Padua, Margherita Cera.
Thank you. Good morning to all of you. It's with great pleasure that I welcome all of you here in Padova, also on behalf of our city mayor, Sergio Giordani, who is unable to be with us today to this Congress of the European Astronomical Society. I really would like to thank Roger Davies, outgoing president of the Society, Lex Caper, chair of the EAS 2025 organizing board, Sara Lucatello of the Padua Astronomical Observatory, incoming president of the Society. But I would like also to mention Alessia Moretti, Marco Gulietskitz, and Simone Zaggia of the Padua Astronomical Observatory for coordinating the local organization, and of course, Bianca Poggianti, director of the Padua Observatory, and Micela for coordinating the scientific organization. Finally, a huge thank you to Roberto Ragazzoni, INAF president, for his generous support. Really thank you to all of you because it's a great honor for our city to host this important Congress in this new Congress Center designed by the famous architect Kengo Kuma, which became the symbol of the innovation in our city of Padova, that is one of the European Capital of Innovation 2023 in the category of the Rising City. So it's very important for us to host this Congress. But Padua, for those involved in astronomy, is not just a city like the other. Here in our university, that has just turned 800 years old, Galileo Galilei taught. He came to Padova in 1592 to hold the prestigious chair of mathematics after teaching in Pisa from 1589. Here, he was staying until 1610, and he always remembered its time in Padova as the best period of his entire life. The legend tells that here in Padua, Galileo made its important discoveries from the top of the Specola, the tower of the ancient Carrarese castle, the home of our medieval senior family in Padova. The tower of the Specola is still the home of the Astronomical Observatory of Padova, one of the most important research centers of the National Institute of Astrophysics. If the Greek scientists remember that Padova period was a period so pleasant for him, however, the reason was above all the great freedom in research as well as in teaching that he enjoyed during this year spending in our city. This reminds us how, for science and research, freedom is a fundamental condition to be able to express the full potential of the same research. Of course, for all of the citizens which are not directly involved from a scientific point of view, astronomy is still shrouded in the fascination of mystery, and there is nothing that appears more unknown to us than the universe. Let me express the curiosity and the fascination that the names of the scientific areas in which this Congress is structured have on me: cosmology, evolution of galaxies, gravitational wave, black hole, the Milky Way, interstellar astrophysics. Each of these areas of study already seems incredible to me, actually. But I think that this fascination for the mystery of the universe is also the reason that motivates you scientists, researchers, and scholars. Astronomers and astrophysicists investigate and interpret phenomena affecting the universe. Through observation and analysis of celestial phenomena, astronomers seek to understanding the origin, evolution, and nature of the universe. This is a path that expands our scientific knowledge, which already has important technological and therefore economic spin-off, like our delegated for the reason Mr. Calzavara remembered a few minutes before, but which the scientific knowledge, of course, inevitably maintains a close relationship with one of the questions that humanity has always asked: what are we really in the universe, and what place do we occupy? This is a question that man has also tried to answer through religion and philosophy, and so for humans it could not be just science, but will always have to do with the relationship between us and the infinite and the universe. So I really want to wish you a good Congress here in Padova, and I really wish you to enjoy the city and the several sites in the city where the universe is, for instance, be painting during the years, and of course to visit the Specola Tower with its important museum. Good work to all of you. Thank you very much.
Now the president of INAF, Roberto Ragazzoni.
Esteemed colleagues, authorities, thanks for all of you being here. I promise to be short, so I want to wish you the great success in this meeting. Not only this is an opportunity for people from all Europe to exchange ideas, to show their scientific results, but I believe mostly for trigger new questions, new challenge, new area of science, new questions that have to be solved in some manner. We as Europe have a tradition in being able to do this all together. Let's land on a comet, and we did. Let's make something strange, and we did. Not very often. Very often has been a success. Sometimes was very struggling, but it's okay. So I hope that, and I wish that during this meeting there will be new questions, new ideas, new proposals for new things to do, new challenges, like is there a chlorophyll on an exoplanet? How is the space metric at Z20 or stuff like that? And this will trigger people to invent, design, build, and operate a new kind of observational astronomy. So my best wishes is for all of you. I will say enough will support all of this. Usually I will say with to a reasonable extent, but in this time I want to say with even a mildly unreasonable extent. So great wishes of a great job for all of you in the coming week.
Thank you. Now the director of Padova Observatory, Bianca Poggianti.
Thank you very much. So I'm Bianca Poggianti, and together with Micela, I was the co-chair of the scientific organizing committee of this meeting. We've been particularly pleased and impressed by the extraordinary response of European astronomers, both for the many excellent symposia and sessions that have been proposed, and for the participation of so many astronomers here this week. The 28 SOC members coming from all over Europe had a really challenging task, choosing among the 155 proposals for symposia and sessions, more than double the previous record, I'm told. As director of the ENAF Astronomical Observatory, it is a pleasure, of course, to welcome you here, and it is an honor to host this annual meeting, which is the most important astronomical meeting in Europe. You have heard many times already that the relationship between Padova and astronomy has ancient and very deep roots, and Galileo is just an example. Astronomy has flourished in this town for centuries, both at the university and at the Astronomical Observatory, which now I have the honor to direct. The observatory was established 257 years ago and currently counts 130 researchers covering essentially all fields of astronomy. You will meet many of them here, both in the hosting committee, but in all the sessions, essentially. And the close connection between Padova and astronomy is visible in many corners of the town, in its art and architecture. And I hope you will have a chance to discover it, as I hope you have already booked the tour of the Specular Tower, where the observatory is located. It is a visit offered to all of you to admire the Specular Museum and the nice views of the town from the top. I want to thank the president of the EAS, the vice president and president-to-be, the council, the annual meeting board, the members of the SOC and of the hosting committee who have worked so hard, Cuoni, all the volunteers, and all those that have contributed to make this happen. I wish you all a very fruitful and pleasant meeting.
Okay, I want to thank you all the authorities for their warm welcome, and then we can continue with the program.
Good morning. My name is Agata Rozanska. I'm from Warsaw, Poland. I'm EAS counselor, and I have a great pleasure to announce the first scientific talk here and the first prize. EAS each year gives prizes, everybody knows, and the first one, it will be Ludwig Walcher Lecture. European Astronomical Society have chosen Roland Bacon for his Ludwig Walcher Lecture, and the prize goes for the development of integral field spectroscopy as a core technique in observational astrophysics and its application to a wide range of problems, in particular galaxy evolution. And I'm happy to start the first lecture, and the title is From Tiger to WST, a scientific impact of 40 years development in integral field spectroscopy. Welcome, Roland. The floor is yours.
Thank you very much. It's a great honor. And I would like to share this with all the scientists and engineers that have participated to this very long development. Okay, so I start with this first slide, which show the scientific production refereed papers by year of all VLT instruments. And now you should see Muse. I think it's a very impressive curve. And it's, to my point of view, really what shows the best success of Muse. Okay, but of course, this was not completely luck, this success. In fact, it's a long story where we have of development, but also success and failure that I'm going to briefly present now. I will try to resume this almost 40 years of development from the very beginning to the long-term future. So, okay, so let's start with the birth of integral field spectroscopy. So to put things in context, in the 80s, spatially resolved spectroscopy was almost only done with long slit spectroscopy. There were a few groups working on scanning Fabry-Perot. Sorry, how to get back? Yes, okay. So I've done my PhD under the supervision of Guy Monet on the modeling of elliptical galaxy on the kinematical property. And at the end of my PhD, we decided to do our own observation. So we went to CFH with Guy, and we performed a long slit spectroscopy in order to test my model. So from this great run, I learned two things. First, having only one dimension is really a strong limitation. And also, I learned that doing observation is so much fun that I wanted immediately to become an observer. So, but I was still a bit obsessed with getting 2D velocity fields. So we went back to CFH with Guy and the Marseille group in order to test, to do it with the Fabry-Perot. But it failed. I think the reason is that Fabry-Perot is scanning Fabry-Perot is well adapted to emission line. But when you work with absorption line, which are relatively low contrast, you need a wide spectral range. And given that you need to scan, at the end, you end up with a very low signal to noise. So it didn't work. So I was a bit still obsessed with that. And we discussed with Guy, and Guy decided that we should discuss with his former PhD supervisor, Georges Courtès in Marseille. So we went to Marseille and we discussed with Georges, and Georges proposed to use a macro lens array. I go too fast. Okay. Okay, so then we went back to CFH a bit later with a prototype. And in June 1987, it's a long time away, the prototype was successfully tested on the sky. So we had to find a name for the concept, and we decided to call it integral field spectroscopy. The instrument was named Tiger, and it worked quite well. So let me see if I manage this. Okay. Okay, so you see, this is the first ever image produced by integral field spectrograph. So we see immediately that compared to a scanning Fabry-Perot, since you have no to scan, in a relatively short exposure, you can see directly the spectra. And so we had the feeling that it was quite a robust method. And then it was really the start of this. So then, the first paper came 2 years after. which I think is relatively short for a very new experiment, since we have to develop everything. And this first paper demonstrates that the Einstein cross is a lens image of a quasar. And we also use the ability, which is something unique to EFS, is to distinguish between the quasar and the galaxy by reconstructing the image with different features, the emission line or absorption line. Then you can really decouple the galaxy with the quasar. Sorry for that. Doesn't. Okay. So then the goal was still to obtain stellar kinematics because this was the original idea. But it takes quite a long time because it's much more difficult to handle. You have to control much better the spectrophotometric accuracy and so on. We also have to develop everything, every tool. And so the first ever stellar velocity field was published in '94 on the nucleus of M31. And this shows that the center of rotation was not completely aligned with the center of light, and more surprisingly, even with the peak of the velocity dispersion, which was quite surprising. But it showed really to the community that it was possible to obtain 2D kinematical maps of the motion of stars in galaxy. And this really attracts the attention of the community. So Tiger has been in operation for 9 years and really demonstrated the validity of the concept. We published 21 papers on various subjects from active nuclei, early time galaxies, up and even on the surface of Mars. The development of the data action system was a huge effort. The instrument was not very stable. We had to realign each time on each run. And the small field and the throughput were relatively low. So were really a strong limitation. And at the end, the prototype was not at all user-friendly. You need the expert for all the operation and the data reduction. So now I move to the first generation with Oasis and so on. So 4 years after Tiger first light, we think we had enough results to propose to build a real instrument, and we call it Oasis. Oasis was based on the Tiger concept, but with a new lens array, larger format detector, and proper mechanical structure, and a fully documented data reduction software. So it was decided to couple it to the AO bonnet at CFH. It was commissioned in '97, 1 year after the adaptive optics commissioning. At that time, not everyone was really convinced that EFS is better than long slit. But for the AO, the adaptive optics work, it was really easier to convince them. Well, the reason is when you work at diffraction limit, of course, the PSFs change very rapidly with wavelengths. So then it starts to be a bit difficult to optimize the slit widths. But in fact, the most important reason is that when the spatial resolution increases, the observed morphology of the source become much and more complex and really do not match the geometry of the slit. So, okay, so maybe. Okay. So when for an integral field spectrograph, the limitation at the end is the detector format. At that time, 2K CCD were really state of the art. And then because you want to sample correctly the high image quality provided by the adaptive optics, you end up with an extremely small field of view. So I was concerned to have such a tiny field of view of 1.5 arcseconds. So we had 4 different sampling to trying to enlarge that. Then we had various spectral resolution because it was a general purpose instrument with different grating, and that was already a large number of modes. But the Marseille group which was working with us, had a scanning Fabry-Perot mode, and then a sort of new mode, which called PTAS, a combination of a scanning Fabry-Perot and a Tiger lenslet mode. And then when we proposed that to the Scientific Council of CFH, they asked to add an Argus fiber mode and then a long slit mode even. So at the end, I think it was a bit too much. But I was a young PI, and you cannot say no. I learned a bit later on. And so we did all, but at the end, fortunately, the other didn't get the funding for the other mode. So only the Tiger mode and the imaging mode were there. So in 2003, CFH moved to a very big, large imaging survey with megacam. And so we moved OASIS to the William Herschel to be adapted to the new Naomi adaptive optics system, which was in development. So at the end, the scientific production of OASIS was modest. And OASIS never found its public and stay a bit like a niche instrument. Was used by a few. So I think there's a few reasons for this failure. First, the EO really did not work as expected. I think the simulation was really optimistic. Second, without laser guide star, because of the need of a bright star nearby the source, the number of targets is very small. Then, given the very small SPAC cell, the instrument was readout noise limited. And there were really too many modes. So for us, it was really difficult to characterize completely each mode. And personally, I think that a PI must have his own vision and sometimes keep some distance with the committee recommendation. So the largest field of view of OASIS was not really bigger than the Tiger field of view. And then I was convinced that there is a lot of science to do with a large field EFS. So it was not possible to put another one on CFH. So I approached Tilde Zoo in Leiden to evaluate if something can be done at the William Herschel. The idea was to do something dedicated to the study of nearby galaxy, not a general facility. We approached Roger Davies, at that time in Durham, and the three of us started the SORON project. It has been a great experience. We built an instrument at Kral in only 2.5 years, and we start immediately the operation at the William Herschel. And then we assembled an international team of young PhD and postdocs. So we performed the first ever EFS survey of 72 early type galaxies. So a sample today of 72 seems small, but it was big at that time and much more than we have been able to do in all the Tiger life. So the SORON survey produced great results. It demonstrates that the kinematics and the strength maps are complex and contain much more information than the photometry. It was followed by a second survey called Atlas 3D, which was a volume-limited sample of 260 elliptical and lenticular galaxies. So surveys are really a lot of impact and generate a lot of follow-up. So really, in a way, establish EFS as the best instrumentation to study nearby galaxy and definitively show that it's much superior than long slit. Many other surveys such as Manga, SAMI, Khalifa were inspired by the SORON survey. So what I learned from the SORON project is that an instrument built for one task and a limited number of modes is always more efficient than the multi-mode approach. And of course, we took risk, but it has paid off. The second thing was good in the SORON survey that we bring together early in the project instrumentalists, observer, and modelers. That really helped to keep the science focus. Because the instrument was similar to OASIS, we thought that the data action system would be far easy but it was not at all the case. Each instrument, each mode is different, and this takes a lot of time. And then I think last but not least, I think we've been able to assemble a very nice team. We keep a very good team spirit, and it was really, I think, something great for PhD and postdoc to build their career. And this is true because a number of them are in this place now. So now I move to Muse. So in 2001, ESO issued a call for a second generation VLT instrument. That was really a great opportunity to develop an ambitious instrument. So I assembled a consortium of 6 institutes in Europe, and all together we start the concept study. So my vision was to build not a spectrograph with some imaging capability, but a 3D instrument with real imaging capability, which means that you need a large field of view, you need a high image security and excellent throughput. And this was not really the case for the first generation. Of course, we want to keep the great spectrographic capability with good spectral resolution and large simultaneous spectral coverage. But I wanted to use what we've learned from the first generation: minimum number of modes, efficient operation, state-of-the-art data reduction, and ability to perform survey, especially for using the guarantee time. And then I wanted to invest a new area, the high redshift. So after 3 years of phase A, the project was approved by ESO. It took us 10 more years to build it. So, as you know, Muse is based on 24 identical modules. It's almost like 24 first-generation EFS. Every problem was multiplied by 24. And thus, we had to planify and manage the project very differently. I cannot say that it was a straight road. As you can imagine, it has been quite bumpy, and we had to face many technical but also managerial challenges. However, we managed to keep an excellent team spirit, and we finally solved all challenges. So in 2001, we had first light in parallel, first without EO, because given the past experience with Oasis, I avoid the project to be fully linked with EO. And then the EO came a bit later with first the wide field mode and the narrow field mode. So I have no time to present this very long phase, but I would like to share with you one very specific moment of this time. This is the day that Muse literally lands to the UT4 platform. Muse was too big to enter the door with the elevator and has to be sent through the slit. At this moment, Muse was hanging 20 meters above the ground. 13 years of effort of engineers and scientists were just there on a cable. Quite a scary moment. But finally, Muse landed on its last spin platform just 30 minutes before the deadline. The deadline was due when the sun is too high, the risk of the sun to enter directly into the dome and hit the mirror. So Muse was unpacked. We checked that everything was fine. And Muse is there and is still there and probably will be there for a long time. And of course, the team was very happy. So I knew that Muse will do so much better than Sauron and Oasis, and that its impact in the study of the nearby galaxy will be fantastic. And indeed, this is the case. But I wanted to investigate the case of high redshift galaxies. In 2001, the landscape was fully dominated by the multi-object, the MOSS, on the 10-meter class telescope. The referees which review our phase science case were not very positive on our proposal, but they basically said that Muse will not do better than the MOSS and will be, at the end, very inefficient, as most of the SPAC cell will just be looking at the sky. Well, I was, of course, in disagreement with this because I thought that the need to pre-select target for the MOSS introduce strong bias and limit the discovery space. I think the investigation of the Hubble ultra-deep field with MUSE that we performed during the GTO is a good example. In this small field of view, MUSE is 10 times more efficient to detect galaxies than the MOS, and even was able to probe a population of ultra-faint galaxies at magnitude larger than 30, which are not even detected in the UDF broadband image. But the power of MUSE in that field, more than anything else, is in its capability to detect extended diffuse emission, probing the circumgalactic medium of high redshift galaxies in emission for the first time, and up to the megaparsec scale for the faint filament. So, contrarily to the long slit, MUSE will not replace the MOS approach, but it has shown that it is very complementary and can probe different populations and smaller scale. So, if you are a MUSE lover, join us in Munich this November. ISO has organized a specific workshop for the 10 years of operation, and it's still time to propose an abstract. So, what's next? MUSE is victim of its success. I think it's heavily oversubscribed. I realized soon enough that one MUSE on the planet isn't enough to satisfy the appetite of the community. There were not many options possible. I looked first to build another one on the north, but finally, the best solution was to build another one on another UT. But rather than building a copy, we propose with Johan Richard to extend the parameter space of MUSE by building a MUSE-like instrument, same field of view, but dedicated to the blue wavelengths. So in addition to maximize the throughput in the blue MUSE will have twice the spectral resolution of MUSE. And then with this new parameter space, MUSE open new science case, in addition to be very complementary to MUSE and offer more MUSE time to the community. The project is led by Johan, and we expect first lights in 2031. What could be the next generation? From the first generation to MUSE, we had to change our paradigm to move from one simple instrument to a complex instrument composed of 24 units. To go beyond this, we need to change our paradigm again. We cannot build the instrument on an existing telescope. We have to build a facility. That is a system where the telescope and the instrument are all built together. This is what we intend to do with WST, the Wide Field Spectroscopic Telescope. In fact, the need of such a facility is one of the priorities of the Astronet EU roadmap. And of course, the MOS community is well aware of that, and they wait for that as the next after the 4-meter class telescope, which are transformed to facility to do that, such as FORMOS, DESI, or WIG. We have seen that MOS and EFS are very complementary. Then, why not merging the two and build a spectroscopic facility with MOS and EFS capability? And to this end, we have defined a very ambitious and innovative facility composed of one telescope and two instruments. So I go briefly in the top-level requirements. So we propose a 12-meter sync telescope with a field of view of 3 square degrees and working in the optical and infrared up to the H band. Then he has two instruments, one MOS and EFS. So there is a MOS low resolution with a multiplex of 20,000, quite big, 10 times larger than we have now, medium spectral resolution, and which operate in the visible. So the extension for the infrared is foreseen later on for cost and also feasibility reasons. There is a second mode, which is the high resolution, which has a resolution of 40,000, quite big for such a big telescope, and still a multiplex of 2,000. So it covers a few regions in the optical. And then there is the EFS. The EFS is a gigantic monolithic EFS with a field of view of 3 by 3 arc minute field of view and spectral resolution of 3,500 and cover the full optical range. So it's more or less mu plus blue mu multiplied by 9. And also the ability, you will see, to work on the mosaics. So there is 2 additional operational requirements. The MOS and the EFS should run simultaneously, and we want to implement target of opportunity in an efficient way at the telescope and the fiber level. And you can see how big the field of view is compared to the VLT and the ELT. And you can see also how big it is on the center, while the MOS is doing multiple configuration. In the center, you can do mosaic on even a very large field of view or go deeper. So this is the current concept design of the facility. Telescope is a Cassegrain configuration with a fast f1 primary mirror, which is based on ELT segments. No need to reinvent the wheel here. The MOS wide field is imaged to the Faber positioner, and the 20 MOS low-resolution spectrograph and the 4 gigantic high-resolution spectrograph are located on the azimuth platform. This is to limit the fiber length. Then the central 13 arc-minute field is sent to a coup de focus via a field selector that allows to select the 3x3 arc-minute. And then on the ground floor of the building, you have the EFS station with 144 EFS spectrograph. And as you can see, and this is because it's a facility, the total volume and cost of the instrument is almost equal to the one of the telescope. This shows why you need to build such a facility. So such a facility will have a very broad science case that I have no time to describe here, but it goes from basically the study of the Milky Way to the cosmology, including the time domain science. So many of them use an interesting combination of the MOS and the EFS that work at the same time to probe different scale or density of source. WSC has a very strong synergy with many other facilities such as Gaia, LSST, Euclid, SKO, Einstein Telescope, and ELT. So the first version of the white paper is already available on the archive, but we are going to produce a second version. And do not hesitate to register to become a science team member to participate to this version. Okay, so WSC is a community effort. It's a very large consortium, as you can see, and an even larger science team. The plan is to continue the concept study for 3 years. We are planning 70 full-time equivalent staff effort on it. So it's an optical near-infrared facility composed of this large telescope, wide field, and 2 instruments. And we think will be a game changer. Because MOS has 20 times the field of view of the VLT, 10 times more multiplex, the EFS are 9 times the larger field of view, and the MOS high resolution of 40,000. This is quite unique, and the simultaneous operation of MOS and EFS allow new science. We have an innovative and sustainable design, and at the end, we think it's low risk because we use mostly ELT technology, and for the rest, we know, of course, we'll have to work on the massive production of a large number of slicer, spectrograph, and detectors. But he has a very broad science case and a strong synergy with existing facility. And in fact, it's the missing piece in the worldwide portfolio of large-scale facility. I think we all collectively absolutely need such a facility. So we are going to propose it to ISO as the next post-ELT large program. The timeline currently foreseen is a decision in 28, first light 35-40, and an estimated cost of 800 million euros. So it has been a long and great story, almost 40 years. I enjoy it so much. This project has given me the opportunity to work with many creative and talented scientists, and I think science is above all a human adventure. In 1987, at the first light of Tiger, I could have never imagined that EFS would become so successful. So thanks again to all those who have been part of this adventure. Thank you.
Thank you, Roland. And it was my unconscious bias that I kept your medal during your talk. I'm sorry for that. Of course, there is a prize, there is a medal. Congratulations. And questions, please. Yes, please.
Thanks a lot for this presentation and the hard work. Just a curiosity, why not red news?
I think we red infrared news, you mean? So that I think is been a bit discussed, and maybe this will happen. It's just the cost of the detector, since you need a large number of detector, that makes such a facility difficult. You need to go to higher resolution because of the sky, and you need to be competitive with space. So we need to look to that carefully before putting such a large amount of money.
So congratulations, Roland, for this well-deserved prize. It's fantastic. I was wondering, what advice would you give to the next generation of instruments builders? What should they bring to be as successful as you were over 40 years?
Just enjoy it. I think I put a number of things. Develop a vision. Work with many people. You cannot do that on your own. So, and yeah, these are long story. You need to be aware of. It's a long story, but I think it's really rewarded if you can do that. And I'm sure there will be many.
So I wanted to ask, why was the velocity center centered in M31?
Sorry, I didn't catch completely your question.
You showed us the velocity map of Andromeda. Why was it off-centered?
For the for M31, I think the idea was, I'm not sure it has been completely concluded this, but there was some wrangling around the black hole that could show this velocity dispersion offset. For the light, I think it was easily explained.
Thank you.
The last one.
Congratulations, Roland. Do you think, I mean, all these new instruments produce data cubes that are more and more heavy and difficult to exploit? So do you think that the techniques that we will have to analyze the data cubes will be at the level of the development of the instruments?
Yeah, I think it's a good question. I think especially if we go to a facility like WST, we know that this must be a major development from the community, because I'm not sure that ISO will be able to do that on its own, to handle this a bit like other big, larger facility. A large fraction of the effort should go into this development for getting this done. So, well, I think it's a time of big data and there's a lot of development. There's no reason we cannot do it, but we have to start that early enough.
Okay, I think we have to move. We have to move. Thank you very much. I think also in any discovery, some luck is needed. As you said, you didn't mention, you didn't even expect it will be such a great discovery. And I would like to advise all of you to go to Specola Museum to see the oldest spectrograph presented here in Padova. Thank you very much. We have to move.
So, good morning, everyone. I'm Alessia Moretti, and I work here at the Padova Observatory. That's why I'm here today, because I'm part of the hosting committee. So, it's a great pleasure to chair these two next talk, which will be plenary lectures, which will introduce you to the very diverse and rich program that we chosen for this year, EAS 2024. The first talk will be given by Luigi Guzzo, who comes from the Milan University, and he's going to talk about the beautiful Euclid data, the status of the mission and its perspectives. Please, Gigi.
Thank you, Alessia. Thank you, everybody. Hello. Good morning. My name is Luigi Guzzo. I'm one of the science coordinators of the Euclid mission. And so I thank the organizers for giving us this opportunity. So I'm here to talk on behalf of a consortium of more than 2,000 people. And it's a great honor. It's a great opportunity. And actually for us is a demonstration of the large expectation that the community has on what Euclid is going to deliver in the coming 10 years. I'll try to show you that Euclid is a project that springs from cosmology, and I will concentrate most of my presentation in terms of what we expect to find on that, but it has an enormous potential for legacy, and so I'm sure it will impact every field that is represented here and will give to people to work for many decades. I think we have to expect something like similar to what the Sloan Digital Sky Survey did from the ground. For me, on a more personal note, is also a great occasion to be here because I graduated in Padua and my family is here. My parents are still alive and live here, so it's a very cheap travel for me to come here. And it's a beautiful city, so I have to give you welcome to Padua also on my side. Anyway, okay, let's get serious and let's try to tame this system, which I've seen is giving a lot of troubles, and I'm very scared because I have a number of animations, which I like animations because they help people to follow the presentation. But let's see. I will try to be very delicate with this. Okay, so Euclid at 1 year, first credits. So all Euclid material that I'm going to show here is done on behalf of the consortium, the Euclid consortium, and has been approved by the consortium. There will be a lot of credits to give. You can find everything you want on the website. You can find beautiful pictures and movies on the ESA Euclid website. Let me just put my clock so I don't get long. The support from the agencies of many countries is very relevant. So the flags that you see underneath are just a compact representation of what will actually fill an entire slide with more than 200 symbols. So let me see how this works. Okay, that's good. So where does this start from? Well, it starts from the beautiful model of cosmology that we have. We have a beautiful model because it's mathematically simple. There is a broad concordance. It's called the concordance model. Basically, there are no observations that contradict this model, although it's physically hard to explain, and there are perhaps emerging tensions which we would like to understand where they come from. What are the problems? The problem is that this model has completely unobserved ingredients. So we see the effects, but we cannot detect them. So dark matter, where are the particles that form cold dark matter? That matter must be cold, otherwise we cannot form galaxies. And also we need dark matter to form galaxies. It's something that, when people say we need dark matter because galaxies rotate too fast. No, not only. We cannot explain the structure we see today without dark matter. There is not enough structure at the CMB epoch that we see in the cosmic microwave background fluctuations, anisotropy of the CMB temperature to form the structure we see today. We need dark matter to drive this formation. We don't have any other theory capable of explaining that otherwise. Dark energy, the last kid in the block, why is lambda so small? Why is lambda so fine-tuned and similar to in density to the matter? That's very strange. It's not something that you expect to happen naturally. So perhaps it's an evolving scalar field, it's an evolving field, a remnant of something that we don't understand yet. We know there are neutrinos. We know neutrinos have no zero mass. We see that from the oscillations that are observed. Cosmology is probably going to constrain the value of the total mass of neutrinos better than ground-based experiments, but in combination with underground experiment, probably going to set the hierarchy to find whether the hierarchy is direct or inverse of the masses of neutrinos. Primordial fluctuations. Everything we do stands on an engine producing fluctuations in the very early universe, 10 to the minus 35 seconds, which we call the inflationary era. What did produce inflation? Is there inflation at all? And then the tensions. There are these anomalies on the Hubble rate and the amount of growth measured, the amount of clustering measured at different epochs. So there is a problem. There might be a problem with the growth. Is this a sign of new physics, or is this simply experimental systematics? Okay. The point for us today is that all these can be tested and measured using galaxy surveys. Galaxy surveys done in different ways. Why? Because the story, the composition of our universe are written in the structure that we see. And we see it in this beautiful example of an embodied simulation. This is only dark matter that you see. Building galaxies inside dark matter halos is another very important problem. But the point is that if you change the standard model, you change this picture, you don't get the structure that you see. So that's why we've been building larger and larger and larger volumes of galaxies, including galaxy redshift or galaxy distances, to reconstruct the three-dimensional structure of the universe. And this is what motivates the new generation of cosmological surveys, what are called stage 4 surveys. You might have heard this label, stage 4. This comes from a paper in 2006, a report, the Dark Energy Task Force report, led by Rocky Cole, which stage 4 surveys are those like Euclid that I'm going to show here, and others that are ongoing, like DAISY. So Euclid, let's come to the topic of today. These doubts, this curiosity is something that we don't understand on the standard model, motivated in 2006 when we start discussing this with other people, in particular in view of the Cosmic Vision 2007 medium class mission call. And there were two proposals. One was the one led by Andrea Cimatti, which I was part for a spectroscopic satellite. The other was Dune for an imaging satellite. And actually, I saw here Massimo Roberto from Space Telescope, who was one of the prime motors of the space proposals. Both the proposals were accepted by ESA. They said, well, great, fantastic. Let's put them together and make one satellite to do both things. And as I will try to show you, this is the beauty of Euclid, the fact of combining two probes that are very different, one looking at the luminous universe, the distribution of galaxies, the other looking at the dark universe, the distribution of dark matter. So the Euclid Consortium was founded and with the task of building the two instruments on board of the satellite and develop the science program and organize and perform the data reduction. So let's look at the two probes of Euclid. So two instruments for two probes. The first is galaxy clustering. We want to measure the statistics of the distribution of luminous objects, and we do this. The simplest and the basic statistic is the 2-point statistics, so the first deviation from a homogeneous distribution. The power spectrum is the the way to look at it in Fourier space. And the power spectrum contains an enormous amount of information, an important information which became a standard tool over the past 20 years or so, are baryonic acoustic oscillations that are the remnants of the acoustic waves that before recombination were produced in the plasma in which baryonic matter and photons were captured. And this gives rise to a specific scale that in the power spectrum is seen as a sequence of wiggles. And this can be used as a standard ruler to measure the expansion history and the distance relations. The other important information you get from the galaxy clustering are the so-called redshift space distortions. This is due to the fact that we don't measure the cosmological redshift only. We measure the combination of the cosmological redshift with the peculiar velocity of galaxies due to the fact that galaxies move towards the density fluctuations. So this factor includes information about the dynamics of the growth of structure. And it's an important diagnostic by itself. So as you see in the picture, if I look at things in redshift space, this is redshift space before it was real space. Of course, this is a simulation. This is the only thing we can see from observations. And this is the way we try to capture this signal. This is a two-dimensional correlation function. And the fact that this is not symmetric, circularly symmetric, is due to the fact that there are these coherent motions towards overdensities that makes it flatter, okay? And this flattening is a way to measure the growth rate of structure. Actually, this brings a lot of information, in particular on distinguishing whether what we see as cosmic acceleration and that we attribute to dark energy, so the cosmological constant, might perhaps hide a modification of Einstein's general theory of relativity when we go to cosmological scales. This actually is a very important feature, this measuring this that we put in the space proposal at the time when this technique was not yet considered to be so reliable. Now is another of the standard probes of dark energy, so to say. The second probe of Euclid is gravitational lensing. So the images of galaxies far away have to travel along their path in between structure. And so the general theory of relativity tells us that light is deviated. And so every image is actually deformed. And you can see this effect statistically by correlating the shapes of galaxies one with each other. And this is what the other instrument, the imaging instruments of Euclid will do. And so you measure a correlation function of these ellipticities, and you see the clustering of all the mass. So you see the dark structure. And this, complementarily to what you do with galaxies, gives you a trace of the growth and the expansion histories. So basically, the goal of Euclid, I'm sorry for this, this is the transportation from one system to another. There are actually two Greek letters, psi and phi, which are the letters by which we describe the two potentials of the perturbed metric of the universe. So Euclid will measure the perturbations in the so-called time factor, that is what you see in weak lensing, which is a truly relativistic effect. It's not predicted by in the theory of Newton. While with clustering, you look at the potential, the so-called Newtonian potential. In GR, the two potentials are the same. But in principle, Euclid can detect differences, and this is what you expect in some theories of modified gravity. But this is not only that. Euclid will look at clusters, cross correlation with the CMB, strong lensing, galaxy evolution, and much more. The Euclid consortium is more than 2,700 people, 14 European countries, USA, Canada, and Japan. And it's, as I said, is responsible for building the instruments and the analysis of the data. So let's take a look at Euclid. There will be, of course, a lot to say, but the time is what it is, and so I will try to take you through the journey, which actually ended exactly 1 year ago. It's incredible, you know, the organizers not only got the right day for this talk, but also the right time. Basically, Euclid was launched 1 year and 1 hour ago, okay? On the 1st of July at 11:12 from Cape Canaveral, and we'll get there. It was a beautiful moment. So the satellite was built by Thales Alenia Space, and the payload, the telescope, basically by Airbus Defence and Space. Euclid is about 2 tons. It includes 140 kilograms of hydrogen as propellant for the motions. And the good thing is that during the launch, the insertion into the orbit on L2 was so precise that very little fuel was used, which now gives absolutely astounding for us predictions for duration of the mission, which might last up to 14 years, which is way above what we expected initially. There's the data downlink is very demanding. Not me, but the expert at ESA had to create a new way to download the data because Euclid is producing enormous amounts of data, as I'll show you in a minute. The telescope is a fantastic piece of optics. It's a coarse telescope, and the quality we are seeing in the images is absolutely amazing. Field of view, well, this is the name of the game of Euclid. The field of view is incredible for space. You know, it's half a square degree, and it's a survey instrument. And Euclid observes simultaneously with in the optical, in the visible, and in the infrared through a beam splitter. So you simultaneously collect lights on the 2 instruments. And here we go. This is the structure of the payload. So here is the satellite is reversed, facing down. So this is the service module where you have the payload module where you have the instruments, you have the visible instrument, and the near infrared spectrograph and camera. The dichroic is here, the light is split, and then it goes into the 2 instruments you see here in this scheme. So basically, we have 2 wide field images plus a near infrared spectrograph, and the size you can see here compared to the size of the Cosmos field, which was the result of a very long survey with HST, and you see we can fit the full moon very easily into the VIS and NISP fields of view, which are co-aligned. The pass bands you see here on the right, you see this is a broad visible band, which was made to be as effective as possible in collecting photons to do the weak lensing. And the infrared camera has three filters, YJH, plus a blue grism and the red grism. So Euclid is essentially the very first panoramic space telescope. And in the wide survey, we are collecting 10 square degrees a day. So at the moment, about 1,000, almost 1,000 square degrees have been covered, 800 and almost 900 at the moment. So the launch 1 year ago from Cape Canaveral on a Falcon 9 SpaceX booster. The launch was beautiful. It was a very, very nice experience, I have to say. And everything went smooth, and the satellite got into orbit extremely, extremely well. And as I said, very little fuel was used for corrections. So these are the first images that we got about a month or something after the launch. This is the visible, one of the first official light from the visible instrument. There are papers on the archive that describe both the project overall, and I will you probably saw already a mention to Méliès et al. 2024, and there's a paper describing this. I just for you to start realizing the difference, this is the field of view of the NIRCam on James Webb Space Telescope. Okay, so you see the complementarity of these 2 instruments. This is the focal plane, 36 CCDs, a beautiful machine. NISP in the photometric as a camera version here, the same field of view. You see 16 detectors. The PSF here is strongly undersampled compared to the visible instrument, where it's very well sampled to do the lensing and benefit of the high resolution of the diffraction limited instrument. Just to show you some comparisons, so we had a couple of early release observation with the very shiny pictures which demonstrated the quality of the instrument and this panoramic capability. Here you see on the background is the Euclid image, and on the top you have, of course, the Hubble image, which is clearly of higher resolution, but this is a single Hubble pointing at the same scale, and this is a single Euclid pointing. So you see again the difference and the complementarity. NISP is a spectrograph as well and produces slitless spectrograph, which to anyone who has done spectroscopy here, including Roger, I think, is a kind of nightmare for data reduction, but it's full of information, and it's something that the space agencies like a lot because it's very simple. You don't want movable parts in space. Unfortunately, the original space concept had a very smart concept that Massimo Roberto proposed, which was using the DMDs. Probably in the future, this might come back. So little mirrors that can be switched on and off to build the slits from a kind of CCD arrays in which, rather than pixels, you have mirrors. So slitless spectroscopy, I want to spend a couple of words here because essentially all of the public images so far by Euclid have been on the imaging. Okay, there is not much published on the spectroscopy, and the reason is that the spectroscopy is very hard, and so we are working very hard to fine tune the pipeline, and I'll show you some results. So basically, what will Euclid do? We do a wide survey using the red grids, covering this range in near infrared. And the target are H-alpha emitting objects. So they will use the H-alpha line to measure the redshifts. The deep survey will target a few fields. We are at 20 next. Thank you. Yeah. And there will be a deep survey. I realize I didn't put a slide. There was no time on showing you how the surveys are on the sky, but the wide survey will cover 14,000 square degrees. And the deep surveys will cover about 50 square degrees, and will go significantly deeper. They will be also used as calibrators for the spectroscopy to understand the spectroscopy of the wide survey. So, as I said, the slitless experiment mode entails significant data processing, but here is a first series of a first example. Basically, we have typically 4 exposures for each object, taken at different angles. This is to reduce the effect of contamination by other spectra. This is an example from the Méliès et al. Paper, the overview paper we just put on the archive. And I got the permission from the consortium to show these, which are unpublished and preliminary high signal-to-noise spectra. Okay, the spectra are not all like this. But they give you an idea of the capabilities, and most importantly, tell you how many of these objects there will be in the final Euclid survey. You can say, oh, these are the brightest. Yes, these are the brightest, but you have 14,000 square degrees of the sky, and so you can imagine, this is a fantastic machine to sample the faint end of the luminosity function. There will be a lot of super luminous objects that cannot be found in any survey, which is just a few hundred square, even a few hundred square degrees. Here's another example, ratio 1.5. You recognize H beta, oxygen 3 doublet, H alpha, and the sulfur 2. So just going to conclude, cosmology is the first target, is the primary science, the so-called primary science of Euclid is the cosmology, and the strength of Euclid comes from the combination of the probes. So combining 2 different ways to measure the cosmological parameters to look at the same universe. And when you go to precisions which are below 1% on the cosmological parameters, you want to be sure that your systematic errors are under control because they will become dominant. And here you see a comparison of the error bars you expect on the shear autocorrelation function from compared between KIDS and EAS, two of the two largest weak lensing surveys nowadays, with what Euclid will get. And just to give you an idea, again from the same paper about the forecast, and this is a paper from the recent paper by the DAISY collaboration that seems to give some hints for the equational state of dark energy to be possibly away from the cosmological constant value, which would be -1,0 in this plot. But the jury is still out because this might be some systematic. So you will look at that. Of course, it's one of the primary goals of Euclid, and this is what we expect. And you see the power when you combine the probes. This is only using essentially this is the 3 times 2 point means that you correlate angular position of galaxies and the shear with shear and shear with galaxies, and then you add the spectroscopic clustering. Okay, so Euclid is on the sky. Most important thing from this timeline, most important milestones are the data release 1, which is will be in June 2026. The consortium is still working hard in final fine-tuning the pipeline, but the results so far are very impressive. I couldn't resist to show you some beautiful pictures before concluding. In particular, I will focus on this Perseus cluster image, which is a single Euclid shot. And the beauty of this is that you can take a small area of this image, and you can zoom in, and you still see space quality imaging with details that are striking. At the same time, Euclid is made essentially to look at very faint galaxies. Like if you go, for example, in this area, and you zoom in, and you see enormous amount of red galaxies that Euclid is going to take also spectra for. Okay, so in conclusion, the outlook is very positive. We went through a year of work. The commissioning and the performance verification were hard. There were problems to solve. We'll mention some now. But the quality of the telescope is incredible. I learned this from my optical colleagues. It's a fantastic diffraction limited optics. The early issues that I mentioned, we had issues with the guiding system. The fine guiding system had to be reprogrammed. So a software had to be written again and sent to the satellite. We have a problem with stray light, which has been solved brilliantly. We have problems with X-ray flares that we unfortunately have to live with. So the sun is particularly active in this period, and so we have to throw away some data from time to time. And we have ice deposition that we are dealing with also very well. That was expected. I think luckily we learned a lot from the Gaia experience, and so the satellite, the optics are equipped with the resistors. We can hit different parts as we like, and the last few weeks show that we have probably understood where we need to hit and what's the most efficient way to get rid of the ice when it accumulates. So, as I said, the wide survey started in February, currently surveying 10 square degrees per day. The goal is to map 1/3 of the sky, and the goal is to possibly unveil the nature of dark matter and dark energy using weak gravitational lensing and galaxy clustering at exquisite precision, and in particular with a much accuracy, so control of systematics. So I want to stress again the immense potential for legacy science. I mean, Euclid will leave a survey of the available extragalactic sky essentially away from the ecliptic and the galaxy in one visible band in photometry, three infrared bands in photometry, and little spectroscopy of virtually everything which is there. And so the first data release will be in 2026. And I think with this, I thank you very much, and I leave for questions. Thank you.
Okay, thank you very much for the very nice talk. We have 5 minutes for questions. While people move around for lunch, I guess. Is there any question from the audience? Brava. Good.
Yeah, I have one question here. Thank you for the nice talk. I'm just curious.
Where are you?
Here.
Okay, hi.
Sorry, I'm hearing also myself. I'm curious how you have eyes on a space telescope. Where does it come from? Can you elaborate a bit on this?
Yes, very good question. Yes, that's a question that us who are not expert in building telescopes learn during this experience. The water comes from the multi-layer insulation layer, the coverage of everything. So this kind of plastic that you see on the top, that includes water. And this water is released slowly for years and years. So there is no way out. What you have to do is to be sure that when you launch it in a very clean way, that you don't pollute the satellite during the launch with dust and other things that would make it worse. But then that water is coming out continuously. The goal is to be able to make this water attached to other surfaces and not on the optics. And in particular, now we have understood that there is one specific mirror. It is called the foldable mirror number 3, which is where the beam is folded into the visible instrument. That is, for some reason, became a kind of cold trap for the eyes. But then the last decontamination was focused just on that, and the result so far is exceptional. At the moment, we don't seem to see eyes coming back. And the interesting thing of this is that the infrared instrument has never been affected by eyes. So we saw a change in the transmission only on the visible side, and the culprit was this mirror. There was another there, yeah.
So I was just wondering if we're not already part of the Euclid collaboration and we had an idea of something to do with the data, how would we go about proposing it and joining or talking to someone about?
Okay, well, so there are two ways. Either you wait for the first data release, because the first data release will be also certified. I mean, everything we will do before will be done to understand that the data are all right and ready for the public release. So the consortium will get the data, the data release package 1 year before. So in March 2025, we get this about 2,000 square degrees that will constitute the DR1, and we'll start working with that. We will start analyzing and produce also some results. So that will be the time given to the consortium both to do a little bit of science exploitation to pay for the more than 15 years of work, but the main reason is that you want to be sure that what you release is sound. However, the consortium is so big, you see all these names, all these numbers, all these figures, not all these 2,700 people formally on the list are active. And I think we're always on the need of active people. So anyone who is interested should contact the Euclid representatives of their country. That's the way it goes. And if they're interested to do something with somebody who is in the consortium, we have a policy for external collaborators. And so the person inside can apply for an external collaborator. Of course, the first thing is that it must be something that adds something new in terms of knowledge, but that can be the case.
Thank you.
Yeah. There's time for a short question. I see a person. Yeah. Thank you. Sure.
Yeah, ciao Gigi. Thank you for the nice talk. It's Adriano. Yeah. So I'm not sure it's a quick question. It's about systematics. Can you comment I mean, you are at the level of accuracy is so tight that there are many systematics, especially even on the theoretical side, that may play a role. I'm thinking about in alignment of galaxies, for instance, these kind of stuff. Can you comment briefly on
Yes.
what keeps you awake?
Yes, indeed, it's not a short question. We could talk for an hour or more. So I will choose and will focus on the spectroscopy, which is my area. And what bothers us in the spectroscopy is the fact that all redshift surveys from the ground had a target sample. So you decide, DAISY is selecting samples from up to a certain magnitude with some color selection, and then they have a catalog. These are the targets. They go, they take a spectroscopy, and then they say, oh, okay, with 100 galaxies, we got redshift for 85. So you know your incompleteness, okay? With Euclid, we cannot do that because we open everything, we get redshift for everything, and so you don't know whether you have not got the redshift because a spectrum is superimposed with another one, so you have confusion, or because there is no galaxy as the right redshift there. And this is particularly nasty for clustering because you easily understand that if you're interested in looking at fluctuations in density to measure cosmological fluctuations, the confusion is also density dependent. Okay, so when you have more galaxies, spectra are more superimposed, and so that goes exactly in the direction of giving you troubles. So this has been one of the main areas of work for the last 10 years, and we have various ways to look at this. You have the deep fields will serve exactly will be doing this in the sense that the deep field, you go so deep that if you select at the wide depth, you are basically 99% complete. You expect to have such a high signal to noise that you hope to be able to understand the wide selection function from the deep. Okay, it's only 50 square degrees, but as I always say, we did a lot of cosmology with 24 square degrees like Vipers on the survey that I led before starting with Euclid, and so I think we can do well with that. At the same time, we need to use simulations a lot, and then one of the great things you can do with the Euclid is that you don't have, so you turn to your advantage the fact of not having a target sample is that you can create the target sample a posteriori. So you can say, I understood that these galaxies, for example, there is a redshift range where you see both H alpha and the oxygen 3 and H beta, okay? And there it's very hard to miss a galaxy or to say, or to mistake H alpha for some other line, okay? So you can have a volume in which you are much safer. And so you can do, okay, let's see which cosmology I get from this sample, which is maybe sparser because you go more far away. And so you have a slightly larger error bars, but at the same time, you know that you have less systematic. So I think this combined approach with different samples will also be very helpful.
Thank you so much. The answer must be much longer. Sorry. We need to cut. So we now move to a very different topic in principle, but at the end it will not be so different, I guess. So we have now Professor Stefano Gattei from the University of Trento, who is not an astronomer, right? And he's not a physicist, he's a philosopher. So he will tell us something about another way to revolutionize our knowledge. And the title of his talk is Galileo's telescopic discoveries and their evidence for the Copernican hypothesis. So please, on stage. L'avviso quando mancano 5 minuti.
Thank you very much. I'm not actually a philosopher, but I'm an historian, which is, I don't know whether it's better or worse. Anyway, I hope you, I thank the organizers for inviting me to give this talk, and I find myself a little bit out of place in with such a big audience of scientists, but I hope you may find something interesting in my talk anyway. So Galileo's researches in astronomy were more than original, they were unprecedented. He was not an astronomer in the sense of Copernicus, Tycho, and Kepler, making observations, devising models, and deriving parameters to compute tables and ephemerides for finding the positions of the sun, the moon, and the planets. Nor did he search for the physical principles governing the motions of the heavens, as Kepler and later Newton did. Most of Galileo's work was concerned with two issues, namely, the refutation of the Aristotelian and the defense of the Copernican system of the world, the Systema Mundi in Latin. His originality lies not so much in what he found or how he found it, as in the way he interpreted his discoveries. Even if his discoveries with the telescope, as interesting as they are in themselves, are of still greater interest for the conclusions that he drew from them, for nearly all of them could be turned to the criticism of Aristotle and the defense of Copernicus, which is exactly what Galileo did in the dialogue on the two chief world system in 1632. In my talk today, however, I will be concerned with his discoveries and interpretations, which, although not as far-reaching as the conclusions he reached in the dialogue, were upsetting enough to anyone who was not already a supporter of Copernicus. So in late 1608, Galileo's friend Paolo Sarpi heard a rumor of an optical device recently invented in the Netherlands that made distant objects appear close. By May of 1609, he must have alerted Galileo. Both were in Padua. It was not hard to make one of these things using spectacle lenses. A plano-convex lens as an objective and a plano-concave lens as an eyepiece. When placed in a tube, the result is a spyglass giving an upright image of 3 times or 4 times magnification. Galileo did this much, and since he wanted something better, he learned to grind and polish lenses. And by August, he made an instrument that would make objects appear 8 or 9 times bigger. He called it a perspicillum, and he arranged through Sarpi a demonstration for the Venetian Senate, on whom its naval application for spotting distant ships was not lost. Galileo therefore donated sole rights to the manufacture of the instrument to the Republic of Venice, which is curious, since he was not the inventor, and Venice could hardly prevent manufacture elsewhere. But anyway. And he asked in return only an improvement in his position at the university and, of course, in his salary. They agreed. His salary was nearly doubled, but not until the following year, after which it would be frozen. This turned out to be a big mistake. For Galileo immediately wrote to his former pupil Cosimo de' Medici, who had just become the new Grand Duke of Tuscany, for a court appointment in Florence, sending him a very fine telescope, such as this one that you see in the slide. By the beginning of 1610, he had made a telescope that would make objects appear 20 times bigger. This is one that is still preserved at the Museo Galileo in Florence. But even before that, he began making observations of the heavens in which it was not so much the magnification as the light gathering and the resolving power of the telescope that allowed him to see what had never been seen before. In about 2 months, December and January, he made more discoveries that changed the world than anyone has ever made before or possibly since. He began with the irregular surface of the moon, went on to the uncountable number of the stars, and then, in early January, found the satellites of Jupiter, which made him resolve to publish quickly before someone else had the bright idea of turning the telescope on Jupiter. And in fact, unbeknownst to Galileo, Thomas Harriot, which you see here, an English astronomer, had already looked at the moon with a telescope. But to look at the moon with a telescope and to see something, or to make sense of what you see, are two different things, as we can see from Harriot's own notes. So you can see at the top what he saw before he read Galileo Sidereus Nuncius, and then after he read Galileo Sidereus Nuncius. Two very different images of the same objects. And then he went on observing through 1610 and offering these and many other images of the moon. In another region of Europe, Simon Mayer, known as Marius, later claimed to have observed the satellites of Jupiter before Galileo, but he did not publish until 1614 in the Mundus Jovialis, which you can see here. And he did not take into account, Marius did not take into account that he was using the Julian calendar, which had remained the standard in Protestant Germany, while Galileo was using the Gregorian calendar. So Marius' claim to have discovered Jupiter's satellites on December 29, 1609, translates into January 8, 1610. One day too late. One day too late, yes. Galileo's first recorded observation dates to January the 7th. Incidentally, this is the title page and facing frontispiece of this beautiful little book by Marius, and you can see Marius on the left, on your left-hand side. And there are two first representations in this image besides Marius himself. So on the top left, you see the first representations of Jupiter with its satellites, and on the table in front of Marius, you see the first published representation of the perspicillum, or the telescope. So Marius was one day too late, but he did eventually get some credit, as the names he chose for the satellites eventually stuck. And this is the page, the two pages from the Mundus Jovialis, in which he decides the names for the satellites, which are Io, Europa, Ganymede, and Callisto, which eventually stuck. No one calls them Medicean stars anymore, but satellites with these names. So, Galileo's latest observation is dated March 2, 1610. 10 days later, only 10 days later, the Sidereus Nuncius, or sidereal messenger or message, appeared in Venice, dedicated to Cosimo II de' Medici, 4th Grand Duke of Tuscany, after whom he named the 4 satellites of Jupiter, the Medicean stars, as I just said. Within a few weeks, Galileo's discoveries were known throughout Europe, and by June, he had resigned his position at Padua to become chief mathematician at the University of Pisa, with no teaching duties. A salary which was higher than the president of the university, and no teaching duties, and philosopher and mathematician to the Grand Duke of Tuscany. After the publication of the Sidereal Messenger, Galileo continued his observations, and in the course of the year he discovered the peculiar shape of Saturn, the phases of Venus, and irregular moving spots on the Sun, all of which he mentioned, along with the periods of Jupiter's satellites, in the preface to the Discourses of Bodies on Water, published in 1612, and then discussed in greater detail in his letters on sunspots in 1613. Within a year of publishing the Sidereal Messenger, Galileo was the most celebrated natural philosopher in Europe. And here is Galileo, as he appeared more or less at the time of the publication of the Sidereus Nuncius, and the title page of this important work on the right-hand side with Galileo's own inscription. Let me now turn to his telescopic observations and look at them in some more detail. Galileo first turned his telescope on the moon and drew a few washes of what he saw. And we have 7 of them. 7 of these original washes still survive, showing the points of light in the dark part, clear distinctions between the lunar seas and the highlands, as they are known now, and several circular features that we know to be craters. He found that the moon has a rough surface with mountains and plains, which was especially evident by examining the terminator between the illuminated and dark portions. For bright points of light were seen in the dark that gradually extended towards the terminator, just as the light of the rising sun first strikes the tops of mountains and then gradually extends down to the surrounding plain. He drew and had engraved 5 illustrations of crescent and quarter phases, 2 of which are shown in this slide. So you can see the bright spots near the terminator and the irregular shape of the terminator itself. Proof that the surface was rough and not perfectly, and the moon was not a cubeball, so to say. The one of exaggerated size, at the very center here, is Albategnus, and others are also identifiable. The large dark region to the left is Oceanus Procellarum, and the roughly circular feature in the upper part is Mare Imbrium, with part of the illuminated rim of Mare Serenitatis extending into the dark half here. Estimating the distance of a lighted point from the terminator as 1/20th of the diameter of the moon, he determined that the height of a mountain exceeded 4 miles. To explain why such mountains do not give the moon an irregular edge, he suggests that the ranges of the mountains overlap to form a smooth curve, and further that the moon, like the Earth, is surrounded by a vaporous orb. Galileo also used the opportunity to discuss a problem he had solved several years earlier, the secondary light of the moon. When the moon is in its crescent phase, the dark part of its body is also faintly lighted, sufficiently to detect the large spots with a good telescope, an effect that disappears around quadrature. After refuting several incorrect causes, as the intrinsic light of the moon, or light imparted by Venus or the stars, or yet again sunlight passing through the body of the moon, Galileo explains the secondary light as a reflected light from Earth. Just as the moon, when nearly full, illuminates the Earth at night, so the early full Earth illuminates the moon. He adds that he will explain this in more detail in his System of the World, a book he was projecting to write, where he will show with many reasons and experiments that there is a very strong reflection of sunlight by the Earth. And against those who exclude the Earth from the choric dance, as he says, of the stars, because it is without motion and light, he says, he will confirm by demonstrations and countless reasons drawn from nature that the Earth is indeed a planet and surpasses the moon in light. This is the most direct statement concerning the motion of the Earth in this sidereal messenger. And it is significant that it is in connection with the secondary light of the moon, which Galileo thus takes as very important evidence that the Earth may be regarded as a heavenly body. What is to be inferred from all this is that the Earth is like the moon, a body shining by reflected light from the sun. And the moon is like the Earth, a solid body with a rough surface, made not of some fifth element of the heavens, but of the same solid stuff as the Earth. Galileo knew that the Aristotelian theory of the heavens was finished, or at least in serious trouble, and that if the solid and Earth-like moon could move about the Earth, the bright and moon-like Earth could move about the sun. None of Galileo's discoveries provoked more hostility and more attempts at refutation than the rough surface of the moon and the explanation of its secondary light. The controversy even extended to the depiction of the moon in the iconography of the Immaculate Conception, drawn from the Book of Revelation, showing a pregnant woman with a crown of 12 stars extending on a crescent moon with its horns downward, in the case of Galileo, that may be either smooth, immaculate, even translucent, according to traditional opinions, as you can see here, or else rough, maculate, and opaque, according to Galileo's description. So this is Ludovico Cardi, a friend of Galileo's, a famous painter at the time, who represented for the first time the Immaculate Conception stepping on a moon like the one described by Galileo in the Sidereal Messenger. Within a space, but there is more, and there is not only the moon in Galileo's the telescopic discoveries. Within a space of 1 or 2 degrees in Orion, we found more than 500 new stars. And to illustrate this, he showed 80 new stars around the 9 original stars in the belt and sword, and 36 within a half a degree of the 6 Pleiades. The head of Orion and Praesepe in Cancer, listed in Ptolemy's star catalogue as nebulos, were found to consist of many small stars very close together. And the most spectacular of all, the Milky Way, whose nature had provoked endless discussion, turned out to consist of vast numbers of stars beyond all counting, grouped into clusters. The implications of the discovery of a huge number of new stars are clear, both for the size of the universe, which makes it implausible for it to turn on itself in 24 hours, as it was believed, and for the number of possible new worlds, a delicate issue, as Giordano Bruno had been burned at the stake only 10 years earlier. So Galileo does not dwell on this too much. On January 7, 1610, so one day before Marius, poor Marius, Galileo observed Jupiter and found 2 small bright stars to the east of the planet and 1 to the west in a straight line parallel to the ecliptic. So you see on the left-hand side Galileo's original notes, starting at the very first line, a D 7 di gennaio, that is today, January 7, and so on. And then you see the published version in the Sidereal Messenger, in Latin, Die itaque septima, January, and so on and so forth. And here's the first representation of Jupiter with 3 little stars, as he called them, which he saw on January 7th. Please note that the thing was so new that he did not even have a way to represent Jupiter. So this circle here is simply the O from the name Galileo that appeared in the title page of the Sidereus Nuncius. So they use the same character there, for lack of a better one. On the 8th, all 3 stars were equally spaced in a line to the west. He wondered if perhaps Jupiter could be moving to the east, although by computation from tables or an ephemeris, it was moving retrograde to the west. The 9th was cloudy, but on the 10th, 2 stars were to the east, and the 3rd, he guessed, was hidden behind Jupiter. At this point, he realized with astonishment that the motion must belong not to Jupiter, but to the stars. But the next night, January 11th, he says that he reached this conclusion. The 3 stars were moving around Jupiter just as Venus and Mercury move about the Sun. On January 13th, Die decima tertia, January 13th, he observed the 4th star and noted that none of them twinkle like stars. That all 4 were moving around Jupiter was confirmed by nightly observation, continuing until March 2, with measurements of their distances from Jupiter and each other in apparent diameters of Jupiter, taken as 1 arc minute, along with estimates of their size or brightness, and from February 26, their passing of a nearby star. All in all, in the Sidereus Nuncius, Galileo published 65 illustrations of the various configurations of each observation. The satellites of Jupiter were a total surprise, first to Galileo, then to everybody else. Their significance, aside from their own interest as the very first additions to the planetary system since the most remote antiquity, was that they showed that a planet could move and have satellites, since Jupiter was obviously moving, and this answered perfectly reasonable objection to Copernican theory, namely that it seemed odd that the Earth could have the moon moving around it while it moved about the sun. So there was at least another center of rotation within the universes, or the solar system as we now call it. On July 25th, 1610, Galileo observed Saturn and found that it looked like a large star with two smaller stars on each side that nearly touched it and never moved. He referred to Saturn as a three-bodied planet, or the planet with ears. He announced this discovery to Kepler in an anagram, which Kepler assumed to refer to two satellites of Mars, since the Earth had one and Jupiter had four. The first published report was in the preface of the Bodies on Water, but by late in the year, the smaller stars had disappeared. Galileo predicted in the third of the letters on sunspots that they would reappear in 1613, and they did. In 1616, Galileo noticed that their form had changed to what later became known to be called, came to be called handles, ansae. He now realized that whatever they were not spherical, and he predicted another disappearance for 1626, which also happened. He suspected their changing appearance had something to do with the alignment of Saturn and Earth, and in this sense he regarded the changes as evidence for the Copernican theory, and possibly with a slow rotational period of Saturn in its own and its two companions. But it was not until 1659 that Christian Huygens gave the correct explanation. Saturn was surrounded by a thin, flat ring, not touching the planet and inclined to the plane of the ecliptic. There was another discovery in 1610 that Galileo could explain completely. That is the appearance of Venus. If Venus were below the Sun, as in Ptolemy's theory, when observed from the Earth, it would always appear as a crescent of greater or lesser size and width. If it were above, which is now seldom mentioned but was still a possibility, it would always appear as a disk. But if it moved around the Sun, as in the Copernican or Tychonic theories, it would change from a small round disk near superior conjunction to a large crescent near inferior. That is exactly what Galileo found between October and December 1610, when he received a letter on the phases of Venus from his former student Benedetto Castelli, to whom he reported his observations. It meant that Venus, and presumably Mercury as well, must move around the Sun. Galileo was not the first to see sunspots with a telescope, nor was he the first to conclude that they were on the Sun and showed that the Sun rotated. He began observing them in 1610, showed them in Rome the following year, and made a careful study of their motions and changing appearances. He mentioned them briefly in the preface to Bodies on Water as a strong argument either that the Sun revolves or that there are other planets moving about the Sun with elongation smaller than that of Mercury, which only become visible when seen against the Sun, or both. In a paragraph added to the second printing, he reported that continued observations had convinced him that the spots are contiguous to the Sun's body and carried about by its rotation in about 1 lunar month. What provoked him into serious publication was a pamphlet called 3 Letters on Sunspots by one Apelles, hiding behind the painting, published by Marcus Welser in Augsburg in early 1612. The letters were sent to Welser in November and December 1611 by the Jesuit astronomer Christoph Scheiner, professor in Ingolstadt, who wrote under a pseudonym on instruction from his order, lest he be wrong and prove a source of embarrassment for the order himself. Hence he used the name Apelles hiding behind the painting from the famous story told by Pliny, showing that he was willing to take correction. Scheiner thought it impossible that the Sun have on its spots darker than the dark parts of the Moon. And since the spots do not return regularly to the same positions, He thought that they are not carried around by rotation of the solar body. Rather, he believed that the spots were many small planets moving about the Sun like Mercury and Venus, although much closer, the possibility that Galileo considered and rejected. One of his arguments for this was that the spots are broad near the center of the Sun, but grow thin as they approach the limb, where, like the crescent phase of Venus, part of the body of the small planet is lighted and not visible against the Sun. Thus, he was aware of the phases of Venus, but he also believed he had independent and superior evidence that Venus moved around the Sun. Magini's Ephemeridis predicted that on December 11, 1611, Venus would reach superior conjunction with latitude less than the semi-diameter of the Sun. Hence, if Venus moved on an epicycle below the Sun, a transit lasting no less than 40 hours should be visible and should be easily observable, since Venus would be moving in the direction opposite to sunspots. But Venus was not seen. As Scheiner put it, and I quote, "She blushed," she meaning Venus. Venus blushed, rushed forward, but we did not gaze upon her nuptials. What follows from this is clear enough, Scheiner says. Even if we were deprived of all other arguments, from this one alone, it would be proof that the Sun is encircled by Venus. Galileo, it's time. Just a few more lines, then I'm done. Galileo received Apelles' letters from Welser in late March with a request for his opinion, which Welser seems to have supposed would be favorable. Unfortunately, Galileo answered in 2 letters in May and October, and following a reply to the first letter by Apelles himself, by Scheiner himself, a 3rd letter in December. All 3 letters by Galileo were published in History and Demonstrations Concerning Sunspots, published by the Accademia dei Lincei in March 1613, a masterpiece of science and invective. I was planning to say more about the clash between Scheiner and Galileo, but my time's up, so I'll stop here. Thank you very much.
Thank you very much. It was very interesting. Unfortunately, we have time only for one question because there are other colloquium going and we need to start at the same time. Sorry. So one question. There? Yes, I am there.
Hi, love the talk. Thank you very much.
Thank you.
Did anyone theorize the existence of craters before Galileo wrote about them?
No, not as far as I know. No, it was. We needed some kind of instrument to see them, and Galileo was actually the first to use a perspicillum or telescope to look at the moon, and the others who actually pointed a similar instrument, even if less powerful instrument, towards the moon, could not, as in the case of Harriot, could not make sense of what they saw. Harriot himself mistook some of the craters or some of the spots on the moon to be tunnels. And so it was hard. It's very hard to make sense of what you see. It's not enough to look at things. You have to make sense of what you see. And also keep in mind that those lenses were far less refined, so to say, than the ones we use nowadays, even the ones we may buy at any shop for a few euros. These were all lenses ground and polished by hand, and they allowed even Galileo, who had the most powerful instrument at the time, because he built it, they allowed him to see only a quarter of the moon. He could not see the whole face of the moon. So it was really hard to patch together the several pieces.
Thank you.
Let's thank the speaker of this plenary session. And we need to leave soon. Thank you very much. And please continue chatting over Slack and during coffee breaks.